Hello. Oh, the mic is live. Thank you all for coming. I'm glad you found the room because, if you ask a web browser, 404 is not found. So here we are. I'm Nat Goodspeed. For the last 9 years, I've been working at Linden Lab on Second Life. During that time, I've developed a sort of fascination with C++ concurrency. You might almost say an obsession, a mania. But I'll let you characterize however you want once we're done. To design a non-trivial program, you start off with pretty broad strokes and a lot of hand waving. You say grandly that this subsystem is going to handle this problem and this other subsystem is going to take care of that problem. C++ is an object-oriented language. It encourages us to compose objects representing various layers of abstraction. These objects rely on still lower-level objects, and so forth. To be able to reason about a program's behavior, it is critical at any given layer of abstraction to be able to gloss over the fine details of the layers on which it's built. Similarly, still higher-level layers must be able to ignore the implementation details of the layer we're talking about at this moment. What you do not want is for the flap of a butterfly's wings in one subsystem to set off a hurricane in a completely different subsystem. Would any of you guys consider a bit of pro bono work to clean up the world weather system? It's huge, it's old, it's massively parallel, and got a lot of globals. I think we can all agree that this is not the kind of unintentional coupling we want in our own programs. This is mom and apple pie. This is programming 101. But programming 101 has been struggling to cope for some time now. When you look at an event-driven program, it's organized instead by when it must return to the main event loop and when it hopes to get control again. And event-driven applications have been with us for decades. Moreover, we're being asked to integrate more and more functionality. Consider type-ahead hints. While the user is typing into some input field, the application matches the partial input thus far against a list of likely candidates. That list is even more useful if it's being dynamically fetched from a back-end service instead of baked into the application. That involves fetching and updating the display in real time while the user is typing. Users have very little patience for an application that periodically freezes up while it consults its back-end host. They want it to be responsive 100% of the time, even if it hasn't yet finished fetching the answer to its question. In other words, users expect their application to handle a lot of different things at the same time, most especially lively UI interaction, along with snappy web service requests. Since C++11, to be honest, since well before then, it might seem obvious that the best way to achieve concurrency is to introduce new threads. You can spin them up and join them. You have lots of available synchronization primitives. You can use package task or promise and future to manage background computation of a value. Because the operating system manages threads, it can transparently do the right thing when you issue a blocking I/O call. It blocks only the calling thread, not the whole process. The trouble with threads is that they're too simultaneous. Threads are truly parallel, not merely concurrent. Sharing resources between threads quickly becomes very tricky. A trivial example is incrementing a counter. We might write counter plus equals 1 and think no more about it. But at machine instruction level, that increment operation might be implemented as read, add, write. And if two different threads happen to try to increment the same counter at the same time, they might both read the value, both increment their respective registers, and both write, when of course the counter should have reflected both increments. And that's without even considering the wacky instruction reordering performed by modern processors. So we need to defend every shared resource in any of several ways. Some of those ways could be expensive. I do not work in an environment with thousands of semi-independent tasks. I personally am more concerned with the racing problems with threads than with their performance implications. But some of you do. And by this time, you're all too aware that as the number of OS threads becomes much, much greater than the number of available cores on the machine, the system starts thrashing because the context switching overhead starts to dominate. Those of you who work in a 32-bit address space with thousands of semi-independent tasks are particularly aware of the cost of stack space. Maybe this is only really an issue with the 386 processor family. As you well know, a typical C++ function call on a 386 machine involves decrementing the stack pointer. So let's look at a 32-bit address space. A clever operating system reserves a pretty good-sized chunk of address space for the process stack, not to scale. It doesn't have to commit all that memory, not yet, not until the program actually uses it. Whoa, big stack allocation there. And the next function call pushes us over the limit. Not to worry. The clever operating system, seeing there's no conflict, simply grows the range of address reserved for the process stack and lets the program continue. This works fine as long as the operating system is clever enough to keep the program's other allocations well out of the way. But what about when you launch a new thread? Again, you don't have to commit all that memory immediately, but you do have to reserve a prudent address range. How about when you launch another thread? There's only one place in the entire 32-bit address space where you can hope to grow the reserved address range on demand for any thread other than the initial one. Once you hit the limit, you're done. Game over. You can't move a thread stack. There are potentially lots and lots of C++ pointers referencing its contained objects. You don't know where all those pointers are. So a clever operating system will reserve a big chunk of address space for a thread, say a megabyte. But you know, there are only 4,096 megabytes in the entire 32-bit address space. And a lot of that is already used for the program code itself and for other data. This approach to stack management may strike some of you as overly simplistic. We could have a fascinating discussion about alternative implementations for a C++ program's logical stack. But the bottom line is the operating system doesn't know them, doesn't use them, and even if it did, it couldn't assume that your application used them. This is still a problem even if your system has lots more physical memory than that. The limiting factor is the 32-bit address space. Corollary is that a 64-bit address process shouldn't really face this problem. There, the ultimate limiting space factor will be the system's virtual memory. I don't know how much longer those of us swimming with thousands of concurrent tasks will have to stay in a 32-bit pool, but for now, it is an issue. Let's talk a bit more about data races and prevention. A straightforward approach would be standard unique lock of standard mutex. When the mutex isn't available, we engage the kernel. The calling thread is suspended, some other thread is resumed on the processor. The original thread makes no progress whatsoever while the mutex remains locked by someone else. And when it's finally unlocked, the OS switches context back to the original thread. I submit that we don't often consider the impact of using threads on the development process itself. There's a way of thinking about potential data races that is a little bit of a step up from what I would consider the industry norm. There's certain defensive patterns, certain idioms that must be learned. You guys are probably way ahead of the curve on this one. This is an area in which, unfortunately, the weakest link phenomenon can really bite your butt. innocent maintenance by someone unused to dealing in these terms can silently undermine the robustness of the entire process. So you make doubly sure to get your code reviewed, right? You all do that, right? Naturally, your reviewer must be someone versed in the potential issues. Such people can be a scarce resource on your development team. A big part of the problem is that the language itself provides very little help. Compilers don't emit, warning, potential data race, at least not the compilers I use. The trouble is that an undefended access to a resource that might inadvertently be shared between threads looks perfectly natural. It looks just the way C++ code is supposed to look. Nothing jumps out to call your attention to it, like a big, ugly reinterpret cast syntax or anything. It's actually a properly defended access that sticks out like a sore thumb. So part of the cost is scouring your code to identify possible race conditions. Depending on how long the code existed before threads were introduced and the weakest link to have maintained it since then, that might or might not be a significant part of the overall development cost. So what happens when you overlook a resource inadvertently shared between threads? 2 words. As you well know, this can take almost any form, from an erroneous counter through program cache. As you also know, a crash is the good case. Appearing to run sanely while producing results that are subtly wrong is the worst possible kind of bug. Actually, even that's too sunny. How about a program that appears to run sanely while occasionally producing results that are subtly wrong? Threads, anyone? As I said, the C++ language does not as yet provide a whole lot of help here. There are a couple of tools available. For instance, Helgrind, DRD, and Thread Sanitizer. These tools instrument your program to try to detect data races at runtime. Thread Sanitizer's homepage states that it typically slows program execution by a factor of 5 to 15 times, while consuming 5 to 10 times the normal memory. Which would be great if it could guarantee a clean bill of health. But you already know that runtime trapping can only catch bugs that you actually drive during that session. With timing problems, it's worse than exhaustively exercising every code path, which is already effectively impossible for non-trivial programs. A guarantee of thread safety would require considering every possible interleaving of each thread's instructions with those of every other. That might make a good basis for a crypto system. So if we need our applications to process both user input and some number of back-end queries simultaneously, but for any of a number of reasons we're dubious about introducing lots of new threads, what other options are available? Classic blocking I/O, or synchronous, is based on a very simple API. You call a function. The calling thread stops dead until the function has results available. In the case of web services, this may take milliseconds to seconds. But the straightforwardness of the API is perfectly aligned with everything we've learned about good program organization. Async I/O, or an async API in general, although I/O is the commonest, is based on calling a function that initiates an operation, then returns immediately before results are ready. The operation continues in the background in parallel with whatever else you're doing in the calling program. Finally, the operation notifies the caller with results, generally by calling a callback function. That's it. That solves the problem. This is how we get more concurrency without adding threads, with all their attendant problems. With a good async API, the completion callback is called at a well-defined time, not between 2 instructions in the middle of the code for some C++ expression. The trouble is, now significant parts of your logic, anything depending on that async result, must be extracted to the completion callback. This can have a disruptive effect on your carefully designed program organization. Suddenly, in the middle of a lower level abstraction layer, you must abruptly return to the application's main event loop. Then you must be able to re-enter that layered logic at the point where you left off. It gets worse. How about when a subsequent async operation depends on the result from the first? How about when a third operation depends on the result from the second? Maybe you're thinking, psh, lambdas, done. Any of you ever seen JavaScript code based on Node.js? Wait, sit down. Please don't run screaming from the hall. I promise I won't mention it again. What tends to happen is that you evolve chains of callbacks, each with a bit of the relevant code, a bit of the relevant data. You start thinking despairingly to yourself, but it used to be so nice. It was all carefully arranged into different subsystems, each with their different layers of abstraction. You might say, aha, how about future then? I can link one operation to another. Have you noticed how there are already proposals creeping in for chaining a subsequent operation only on error or only on success? How about a generalized conditional chaining operation? Could we introduce a looping construct? We're trying to layer a whole new language on top of C++. We've already got four: the preprocessor, the runtime language, template language, and context-aware language. Reports from the C# trenches suggest that chains of then are not much more fun to maintain than chains of plain old callbacks. You might say, aha, how about state machines? I can build a machine class that manages instances of state classes. Each new entry transitions to the next state. We even have a couple Boost libraries for this. I've been there. Trust me, it gets opaque pretty fast. You have to reverse engineer the state transition table to figure out what should have been obvious control flow. You might say, but how about a big switch statement? You set an int representing state. Every time you re-enter the function, you immediately switch on the state variable. If you cleverly lay out the case values so that subsequent states are adjacent, and if you squint a little, it even kind of sort of looks like normal C++ control flow. In fact, courtesy of a bit of preprocessor magic and one of the odder syntax anomalies from classic C, Boost.Asio supports a pretty veneer over the big switch statement. It's called Duff's device, and in fact, Boost.Asio is only one of a number of readily available implementations of the idea. Using that, your function looks even more like normal C++ control flow. No squinting required. The trouble with this is that it obscures the fact that you're actually returning from and re-entering the function every time. Local variables get reinitialized every time. Any state you would have kept in local variables must be moved somewhere else, say a heap struct. In fact, Microsoft Visual Studio 2015 introduces compiler support for this very concept. For a resumable function, it generates code that, in fact, stores locally declared variables in a generated heap struct. It implicitly performs the big switch statement for you. This is kind of sort of great. As long as you're working at a single layer of abstraction, it's all you need. Where it has difficulties is in supporting multiple layers of abstraction. The caller of each resumable function must be aware that it might either produce a result immediately or return, nope, not yet. You might be thinking, I know, pick me. I know where this is going. Boost coroutine. And you're close, you really are. But I will show you a still more excellent way. Boost.Fiber library is the best way I know to organize code already based on async I/O. Why the qualification? Why not just say the best way to organize code, period? It's because of blocking I/O. Code that wants to share its host thread with other fibers must avoid making any calls that will block the whole thread. When you call, say, receive on a socket, control enters the operating system. It doesn't return until data have arrived or the socket is closed. It doesn't pass control to the fiber library to say, got anything else to keep busy with in the meantime? But once you're committed to using async I/O, you're good. Fibers are independent threads of execution, being very careful to use that phrase in the sense intended by the C++ standard. But in any other context, whenever I say thread, I mean an operating system thread. By userland, I mean that the operating system is not involved in context switching between fibers. This means that a fiber explicitly gives up control. It suspends, allowing other fibers to run. Cooperative suspension has another important implication. On a single processor system, of course, at most one thread can be running at a time too. But OS threads use time slicing to interleave thread execution in a way that, from the code's point of view, is completely unpredictable. You don't know when code on some other thread might touch a shared resource. Cooperative fiber context switching means that application code can know that it's not being unpredictably interleaved with other fibers on the same thread. Code accessing a shared resource can know that no other fiber on the same thread is trying to access that resource at the same time. Of course, the scope of this exclusivity is within a given thread. If you share a resource between fibers running on different threads, you have the usual issues. Fibers use what ISO has recently been calling suspend by call or suspend downwards. I'll say more about that in a minute. Like standard thread, like a Boost coroutine, each fiber runs on its own separate stack. Asymmetric coroutines, like Boost coroutine, are great when the application has a kind of handshake relationship with a coroutine. A generator is a particular example. Application code starts one up, talks to it for a while, and then destroys it. A fiber doesn't necessarily have the same close relationship to the code that launched it. It's particularly valuable in a fire and forget kind of scenario. Some function f launches a fiber, expecting the new fiber to continue running even after function f returns. If you wanted to try to build such a thing using Boost coroutine, you'd need to introduce some kind of manager to own the coroutine instances. When a fiber context switches away, it does not specifically resume its invoker, unlike a coroutine. Instead, it engages a scheduler to decide which fiber to resume next. You can think of the fiber library as coroutines plus a manager plus a scheduler. If you're one of those people swimming with thousands of concurrent tasks in a 32-bit pool, you may be thinking, but stacks. So yes, each fiber does have its own stack. That's one of the strengths of fibers. And you still can't move them. I just have a couple of things to say about fiber stacks. First, unlike with standard thread, you can explicitly specify the stack size for a new fiber. I'm not a fan personally, because how do you know? How do you know your prior analysis is still valid after the last round of maintenance? How do you know your QA caught the deepest recursion case on each fiber? The fact remains that if you must fine-tune your stack consumption, you do have that knob. In fact, if you want still finer grain control, you can provide your own stack allocator. I'm more enthused about the ability to engage compiler innovations such as segmented stacks. It's a classic time-space trade-off. When you set the slider to fast, you use more space. When you set the slider to small, you use more cycles. But here's the point. You can leverage technology like this because fiber stacks are managed by userland code. You don't need the operating system to grasp the concept. Several different people have suggested hey, why not use Microsoft Resumable Functions as a back-end implementation for fibers? Then the whole issue of stack allocation vanishes because they're stackless. I could pause here to let you guys work out exactly how to make that go. I have no doubt that many of you are brighter than I am. The world would be in your debt. So what's the problem? Resumable functions suspend by return or suspend up and out. Fibers, like stackful coroutines, suspend by call or suspend down. A fiber calls some function. That function calls another function. That other function might choose to suspend transparently to the caller. In practical terms, the caller of a resumable function must always be prepared to deal with a not yet answer. Standard future is one way to express that. The co-await keyword is the magic syntax that wraps up that ambiguity. The answer is not yet available. I myself must suspend until then. But every resumable function that might suspend must be able to communicate that ambiguity to its caller, which means that its caller in turn must be prepared to suspend. It's viral. Every function in the call chain must have its signature and its body ready to propagate that possible suspension. Then every function not in that call chain must also change the way it calls any of the affected functions, and outward it goes. I don't know about you, but in our organization, QA is a scarcer resource than developers. If I fix a little bug in a leaf function, and in the process change the semantics of 30 functions at 5 levels of abstraction, that's going to cost. So what do we have to retest? Well, everything. You could say, well, if resumable functions require pervasive annotation, clearly the set union of resumable functions and fibers would be to require pervasive annotation for fibers too. But no, I use fibers because I reject pervasive annotation. If that was your solution to unifying fibers and resumable functions, why bother? What does it actually buy you over resumable functions on their own? In case you haven't yet guessed, I strongly believe in the benefits of having a stack for each fiber. Most importantly, they give us the ability to write code that looks and acts just as if we were performing classic blocking I/O. We get to keep our clean subsystem design with our layers of abstraction. We get to keep our local variables. You might have wondered, well, what about thread local storage? Isn't that going to be shared between all the fibers on a thread? It's true. I might point out that this can be useful. They share it without racing for it. Some functionality wants to be thread scope rather than fiber scope. You might be interested to know that sharing thread local data is typical for present implementations of other fine-grained concurrency, such as GPU or SIMD support. But so far, I've gotten what I want by using local stack variables instead of thread local or fiber local storage. So yes, there is fiber local storage. The Fiber API is based on the standard thread API, reflecting the role of fibers as userland threads. It supports the usual suspects. In addition, we get these fiber-aware communication queues. As you might suspect from their names, a producer fiber can push an arbitrary number of items to an unbounded channel at risk of arbitrary memory consumption. A bounded channel imposes a user-specified limit, suspending the producer if it tries to exceed that limit. But I'm not going to walk you through each and every one of these because, quite aside from the fact that you can read about them yourself, the point of mirroring the thread API is you should be able to infer their semantics from prior knowledge of the thread API. So why all the duplication? Why do we need fiber variants of these things at all? It's because the standard implementations block the entire thread. As I noted earlier, if you're trying to run more than one fiber on a particular thread, you pretty much want to avoid blocking the thread. The fiber library provides objects and operations that block just the calling fiber, allowing other fibers to continue running on that thread. I might also point out that fiber context switching is far lighter weight than thread context switching. But wouldn't it be cool if we could customize the way that standard library operations suspend? Then we wouldn't need redundant implementations of all of these things. I'll leave that as an exercise for you guys. What I'd rather talk about are usage patterns, how to integrate the library to solve problems that you actually face. For starters, how about Async I/O? I keep talking grandly about how fibers let you write code that looks and acts like you were using classic blocking I/O. I talked about the necessity to use Async I/O, but isn't there kind of an impedance mismatch? Callbacks push, blocking functions, return results. So let's work an example. Here's an API with an init read call accepting a callback. Here's an adapter. We declare a promise of standard string. We capture that promise as future. Then we pass to the init read function a lambda that binds our promise using initialization capture. The lambda's signature matches the callback required for init read. Then, since init read returns immediately, we call future get. This blocks the calling fiber until the future is fulfilled one way or another. Remember, this is a fiber future. Eventually, the operation completes and the lambda is called. If the past error code indicates success, we can call promise set value with the past data. But if the operation failed, we can instead call promise set exception. Either of those calls will wake up the future get call. If it was set value, our read function just returns the past data item. If it was set exception, get throws that exception. Does that seem like a lot of boilerplate to adapt a callback? But it's localized. That's part of what I like so much about having a stack. Encapsulation just works. Then there's non-blocking I/O. For instance, you can set a socket in non-blocking mode. If there's no data present, instead of blocking, a read operation returns E again, or E would block. That's great, but what then? You don't get a convenient callback. In practice, you have to keep polling. Here's an example non-blocking API. Notice that in addition to returning an error code meaning no data yet, this read method might also return less than the desired length of data. In other words, in addition to polling until it returns an actual length rather than E would block, you might also have to keep polling past any number of additional E would block returns until you've retrieved the desired data length. Here's an adapter. We'll call it read chunk because it might only read part of the desired data. It calls the non-blocking read API, and as long as the non-blocking read keeps returning E would block, we yield to other fibers on the same thread. If your other fibers have too little work to do and your non-blocking read takes too long, you might actually consider sleeping the fiber instead of just yielding. We return when either we get a legitimate length or some other error. But of course, that length might still be less than the desired length. So here's a wrapper around read chunk to try to read the whole desired length. Until we've read the full length, call read chunk again, and break if EOF or error. As long as we keep getting success, append the current chunk and loop back to check again. I know perfectly well that there are more efficient ways to concatenate string data. That's not the point here. We return when either we've read the desired length or we get some kind of error. Remember, it won't be E would block. And finally, we can wrap all that up in a nice application-facing function that's guaranteed to return data because it throws if it gets an error other than EOF. It doesn't strictly have to be a separate function from read desired. I'm just pointing out yet again that you can layer these idioms as needed. One of the nicer extensions you've seen floated around futures is the ability to trigger some action on fulfillment of the first of an arbitrary number of futures. For instance, you might want to fire off redundant queries to several semi-reliable backends and accept whichever answer arrives first, discarding the rest. But like future then, that feature is callback-based. Consistent with our quest for cleaner application architecture, let's invert that. Let's say we want to launch some number of functions, each on its own fiber, each of which will wait until it's done. We want the calling fiber to wait until the first of them returns. Not necessarily the leftmost one, but the one that finishes soonest. So this will be a wait any function. If, in fact, we're sending off redundant queries, we're probably reusing the same function, just passing it different arguments. But for fun, let's pretend we might have to invoke different functions. The result we want is the function's return value. I'll present a container-based wait any implementation only because it takes fewer slides than a variadic one. Of course, the return types must all be compatible. And just to raise the stakes, let's say we have to allow for the possibility that one or more of the task functions might throw an exception. We want the first successful result. I'm going to present this function in 2 acts because it's going to be tricky enough to squeeze everything onto a slide. Since this template accepts an arbitrary sequence container of functions, I'm going to make the caller explicitly specify the desired return type. The key is that we're going to collect futures representing the result of each function. Make an unbounded channel of those futures. We use shared pointer because wait any is going to return before the last of the fibers completes. That's the whole point of wait any. We loop over the functions in the container, counting them as we go. It's an arbitrary container. It might or might not have a size method. For each function, we launch a fiber with a lambda binding the function and the channel shared pointer. We detach the fiber immediately. That's a common pattern. That distinguishes a background fiber versus one that you might join later. In the lambda body, we instantiate a package task for the bound function. Package task is a wrapper that runs a function, capturing its return value if it succeeds or its exception if not. Then we directly call the package task. This is a somewhat unusual use of a package task. Normally, you might think of launching a package task on its own fiber, using its future to wait for results. But here, we're already on a new fiber. The point is this. We want our lambda fiber to wait until the bound function either returns or throws. If we were to immediately push the package task's future to our unbounded channel, then wait any would always prefer the leftmost function, not necessarily the one that completes soonest. So we delay pushing the future until we know it's fulfilled. Only when the package task completes, only when its future has been fulfilled, either with the result or an exception, do we push it to the channel. So far, so good?
Are we only using future to have the variance between the error code and the result here?
Yes. The question was, are we only using the future to capture the distinction between the return or the exception? And the answer is yes. But it's convenient that package task will grab that for us. Okay, we've launched a bunch of fibers. In fact, exactly count of them. Now for Act 2. We're going to loop at most count times. Why is that important? Because if every single one of count functions throws an exception, we could find ourselves trying to consume a value from a channel that has no more producers. That would turn wait any into wait forever. Assuming we haven't yet exhausted all hope, we pop the next future from our channel. Naturally, this causes wait any to block until that future is pushed. Then we check whether that future was fulfilled with an exception or a value. The exception pointer returned by future getExceptionPointer will be null pointer unless that exception was called. And we know this future is fulfilled. Once we know the future is fulfilled with a value, we can close the channel. That means that no subsequent producer fibers will succeed in pushing values to it, which is fine. We only want the first. And then we can return this future's value. Of course, if we really do burn through count futures and every single one of them contains an exception, we should probably communicate failure to our caller somehow. Naturally, it would be helpful if we captured one or more of the exception pointers from the fibers. This is just a placeholder. You might think that wait all would be only a slight revision to wait any. And in fact, you could implement it that way. But I have to show you a variadic implementation that I think is just really cool. Since wait all necessarily waits until the last of the functions has completed, you don't have to worry about reordering them. You can present results in the order the functions are passed. In fact, you can just state the type of the result you want and return the whole thing, bam, in one swell foop. In fact, and I think this is seriously cool, you can even pass functions with heterogeneous return types and collect the results in a struct. So all we have to do is make a bunch of async calls, then pass all the futures down to a helper function, which merely initializes the desired result type with the results from the past futures. Tell me that isn't seriously cool. Just for grins, why do we even need the helper function? Why couldn't we use this implementation instead? It's because of the compiler's implicit iteration over the argument pack. This implementation makes a single pass. It launches the first function on a separate fiber, then immediately waits for it. Then it launches the second function on a second fiber, then immediately waits for that. In other words, the implementation above serializes the past functions. It's effectively the same as this implementation, which doesn't even attempt concurrency. With this implementation, you get two different passes through the argument pack. The first pass launches all the fibers, collecting all their futures into another argument pack, over which the helper function makes a separate pass to wait for each of them. Notice the similarity to the loops in Act 1 and Act 2 of the wait any function. I will now share with you the mystical incantation to integrate a classic event-driven program with the fiber library. That's it. That's all you need to do to ensure that the fiber library can divert some cycles to the fibers you've launched. In general, the rule of thumb is just make sure you call this fiber yield often enough. If there are no other ready fibers, it will return quickly. But if there are, it will run each of the ready fibers until its next suspend point. I want to point out something about that call that might not have struck you. For most purposes, the main function and the functions it calls can be treated the same as a fiber that you've explicitly launched. You don't have to move your event loop into an explicitly launched fiber in order to be able to make that yield call. The same is true for a function launched as a new thread. It's simply the default fiber for that thread, just as the main function runs on the default fiber for the default thread. But what about when the main loop is inaccessible, embedded in some other application framework? We'll use Boost ASIO as an example, even though there's more to say about integrating specifically with Boost ASIO. A typical application performs some setup, then just passes control to IO service run. The run call won't return until application shutdown. This illustrates a pattern we see with a number of application frameworks. You have no direct access to the driving loop. One approach is to intercept control with a callback each time around the embedded main loop. With ASIO, you can effect that by continually reposting a handler that calls this fiber yield. Of course, you have to get the ball rolling initially. A potential problem with that approach is that when all the fibers are blocked on pending I/O, so the I/O service has no ready handlers, ASIO and fiber could just spin the thread's CPU, passing control back and forth to each other. If the framework you're dealing with supports timers, ASIO does, but that's just our example, you could use a timer instead. That trades off busy spinning with responsiveness to I/O completion. The framework you're using may or may not manifest this spinning issue. One of the implications of a userland fiber scheduler is you get to play too. The library's scheduling algorithm is a customization point. All you have to do is derive your new scheduler from the sched algorithm abstract base class and pop it in place with use scheduling algorithm. For understandable reasons, this must be the first fiber API call on a given thread. I'm not going to take you through the details right now. Just know that there are several different examples in the library's examples directory. For instance, your custom scheduler can associate custom properties with each fiber. One of those examples introduces a priority property and makes the scheduler honor the relative priorities of different ready fibers. That's one obvious use case for this kind of customization. Another example shares a group of fibers among participating threads. The next ready fiber is run by whichever thread calls next. That about wraps up what I wanted to share with you today. One additional point of interest, the Boost.Fiber library will be part of Boost 1.62, which will be released any day now. It's out in beta 2. And I'll entertain questions. The more entertaining, the better. Yes? The question is, do fibers use all of your cores or are they limited to one CPU? And the answer is, all the fibers on a given thread are going to behave just as if you were running all of that code on that one thread. It does not increase your core utilization. One way of getting the one-to-many effect, or the N-to-M effect, as it's sometimes called, is to share fibers among threads in the way illustrated in the examples directory of the library. But fibers share control within a thread, typically, and you have to use a custom scheduler to get them to migrate to other threads. Other questions? Yes? It is not part of Boost 161. It will be part of Boost 162. Thank you for your patience. Oh, wait, there's a question. Performance comparison. So I don't usually lead with this because for me, fibers are more about maintainability of my code than they are about performance. However, I think the numbers look pretty darn good. Now, I will say this, that I don't believe fiber context switching will compare favorably with Microsoft resumable functions, which, as you probably saw yesterday afternoon, can be optimized out to crazy minimalism. But I think they hold their own pretty well with regards to other concurrency frameworks in userland space. Okay, I see two questions, the one in the back first, and then...
Does each call to yield use more stack? So can you get into a situation where you're kind of yielding to different fibers and using more and more stack?
Okay, since I don't have to repeat that question, I won't. No. What happens is that when you launch a fiber, it gets a stack. And thereafter, yielding between fibers only switches between the stacks that exist. There isn't an increment in stack usage with each yield. And then there was another question midway back towards that person.
So hypothetically, could a standard library implementation of std thread be based on userland threads, a fiber style implementation? And could you eliminate the redundancy that way?
That's a really excellent question, and the answer is that there exists an implementation that does something like that. You have heard of HPX from the Louisiana State University. It isn't based on fiber, but HPX thread is actually, and I'm not entirely sure how they accomplish this, but HPX thread uses their own lightweight context switching and will scale outward to use OS threads when necessary. So the answer is it is certainly possible to do that. And in fact, the HPX people ask, why would we need a fiber library when all we have to do is make the standard thread library be lightweight? It's a good question, but until the standard goes there, we have Boost.Fiber. Wow, okay. So, okay, Robert.
I have one simple question about this chart. One column that I think I expect to see but I'm not seeing is if the same application is, since the interface is almost identical to that of threads, if the same application is rendered in threads versus fiber, what's the difference in performance?
Okay, the question was, why are we not seeing in the performance chart a column for plain threads as opposed to these other technologies? I think that it's because it's orders of magnitude more expensive to context switch threads. And I think that Oliver deemed that it wasn't even worth, presenting the comparison.
100,000 threads is a little much. Oh, I just wanted to ask if you've actually looked what makes Haskell an order of magnitude faster.
I have not looked. The question was, have I looked to see what makes Haskell an order of magnitude faster? I have not. Thank you. It might be that everything is lazily evaluated, so it just didn't evaluate the things that were not being looked at by the benchmark. Oh, one more over here. How much does this?
Latency gains.
With the what case?
So the CPU usage is supposed to be increased at least a little bit. So do we have any numbers about that? Compared to normal threading.
Okay. So if I understand you, what we're doing is we're using each thread more efficiently than if we were waiting in a particular thread. Kind of depends on your application mix. The fact is that you can keep a thread busy with stuff you're doing in fibers while a particular operation is suspended, but you're not blocking the thread waiting on that operation. But the reason that we benchmark with specific algorithms is because it totally depends on your application mix. Okay, well, thank you all for coming. Glad you found it.